ஏதோ மாறு கேக்குது கேக்குது கேக்குது
பாடுறா.
டிவி
ஹலோ பண்றது.
ஆயிரும் அவருக்கு புரியுது இதுல mic ல off பண்ணு.
இரு, இரு, இங்க
இந்த mic தான் off பண்ணு.
அன்மியூட் பண்ணணும். எடு.
இங்க இருக்கு the host would like you to speak இருக்கு. unmute கொடு.
அவ்வளவுதான் அன்மியூட் பண்ணிக்கலாம் அவளை. இப்ப
இருபது.
இந்த idea.
ஓகே
இப்ப எப்படி இருக்கா? இப்ப எப்படி இருக்கா? நீங்க என்ன பண்ணணும்னா உடனே ஷேர் ஸ்கிரீன் போயிட்டு இதெல்லாம் ஒண்ணும் பண்ண தேவையில்ல.
இது நம்ம எப்படி போடலாம்
இதோட என்ன பண்ணலாம் திரும்பி பாஸ் ஷேர் லெட் மீ ஷேர் கொடுத்துட்டு இல்ல பாஸ் பண்ணி தான் வச்சிருக்கேன்.
சேஞ்ச் பண்ண
சேஞ்ச் பண்ண வர ஸ்டாப் ஷேர் கொடுக்கணும். டேய் ஃப்ரீக்வென்சி அடிக்கணும் ஆஃப் பண்றத. டேய் நீங்க தான்டா குதிர ஆஃப் பண்ணாரு. நீனும் திட்டு வாங்குவதற்கு என்பதற்காகவே செய்வது போல.
As you are on behalf of Ryan Harrison, I on the police and the fear of facing so disease. Change the stereotypes, leading to serve as a part. Regular and stable planting. Regime letters, electrical program, advancing from the knowledge. His academic journey includes early Bachelor of Science, Master of Science, and PhD, Bachelor of Science. Following his doctoral fellowship at Harvard College of Poetry, postdoctoral fellowship at Harvard College of Poetry and MIT. He embraced the cause of orchestra in the 1991. In science, including co-ordinating like film apps like Korean and World Apart, as well as exploring trade and science in childhood, which is the way of relevant life, whether astronomer, ghost mechanics, and to be baptized and extraterrestrial and I was very congratulated by one. The reply for start on the water start 2000 by first I always want to as what fun. Yes, the role of reactor of reacting is a very high concept in the society of values observed from the development books of various classified Svega, Kimba, region feature, and then all of the solar particular environment which was so needs not for the thing, personal joy.
Let's create a modern cost. Even beyond serving. But how efficient it keeps the technology through this installed. What development is progress for it. If one is if they got now maybe you know sleeping for long. Well, I got it. Further, only something is
You're recording, you're recording, you're recording, you're recording. That's a fun. Hello, 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 hello.
So that's all anything that we do. Okay. இல்ல நீங்க சொல்லு போலடா திரும்ப இதுல இருக்கு சொல்றியா இதுல ஆனா ஸ்டுடியோ போட்டு அது வந்து போனாங்க அப்ப என்ன வாய்த்தது ரைட்டு டிலே தான் ரொம்ப சொல்ல முடியாது எனக்கு கேட்குது ப்ரோ மீட்லாம் நல்லா ஸ்மூத் ஆகுதுமா ஒரு மீட் ஸ்லோவா ஆகுது
கேக்குதாடா?
மீட் சம்பந்தம் யூடியூப் வரலடா ஸ்கிரீன்ல ஷேர் பண்ணி ஸ்கிரீன் ஷேர் இல்லையா தான் வந்து எந்த ஸ்ட்ரீம்ல வருது அது யூடியூப்ல ஓடுது ஓடி அது நம்ம செஞ்சுட்டு அது கனெக்ட் ஆகல வீட்டுல இருந்து வருவாங்க Hello. ஒரு இன்ட்ரெஸ்ட் ஆகும்ல அதுக்கு வச்சிடும் ஆஃப் பண்ணிருங்க மைக் ஆஃப் பண்ணி ஆக்சுவலி ஆஃப் பண்ணி திரும்பி பண்ண பாக்குறேன் எக்ஸலி என்ன சொல்ல நம்ம ப்ரிப்பேர் பண்ணி பண்ணல இதெல்லாம் லைவா தானே இருக்கிறேன் வந்து லைவா தானே இல்லையா அங்க ஷேர் பண்ணிக்கலாம் ஒரு செகண்ட் இல்லையா 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 சரி மக்கள் எல்லாம் இன்னும் போகலாம் ஒரு செகண்ட் பல செகண்ட் இல்ல இல்ல போலாம் நான் இப்ப அது வந்து டிஸ்பிளே டிஸ்பிளே இல்ல அது எதுல கனெக்ட் ஆகி அதான் HTML எப்படி கனெக்ட் அப்ப நான் படிச்சது இங்க பாருங்க காலேஜ்ல இன்டர்நெட் ஆமா நானே இன்ஸ்டன்ட் இல்ல கண்ணு என்ன ஆச்சு மாறிடுதா கேட்க மாட்டேன் இப்ப அப்படி இன்ட்ரெஸ்ட் அதான் சொல்றேன் இது ஓகே அவுட் வர மாட்டேங்குது
கேக்குதா?
இவர் இங்க ஸ்கிரீன்ஷாட் ஸ்லோ ஆகும் ஃபாலோஸ் எடுத்து லீவ் லைக் போடுறது சும்மா தான் ஸ்கிரீன்ஷாட் அதுங்களா புத்தாண்டது இப்போ வந்து இங்கே வந்து இன்செப்ட் ஃபார்மட் வந்து இது பண்ணு ஸ்கிரீனை பிரிண்ட் பண்ணு என்ன பண்ணுவோம் ஒரு நடக்கிறது இன்னொரு ஸ்கிரீன்ஷாட் பண்ணுவோம் நார்மலா ரூம் ரெக்கார்ட் இல்ல அப்புறம் இல்ல வி ஓன் போடுறோம் அதான் கண்டிப்பா நான் ஒரு
For 1 hour or so, and following which we will have a question and suggestion.
அங்கிருந்து போறதுதான் பிரச்சனை அந்த டிலே என்னன்னு பாத்துக்கோங்க ஆல்மோஸ்ட் இப்ப வரும்
Hello, கேக்குதா?
அந்த ஸ்கிரீன் நீ போன மை பீப்புள்
Hello?
அதான் அந்த ஸ்கிரீன் ஆஃப் பண்ணிடுங்க சும்மா எதுவும் அட்மிட் இந்த ஆடியோவே ஒரு ஓகேவா தாராளமா போகணும் நான் பேச சொல்றேன்
என்ன சொல்லவே இல்லை. ஃபன் பண்ணிட்டு இருக்கேன்.
in honor and privilege to propose the vote of thanks on this memorable occasion. I take this opportunity to express my deepest sense of gratitude to our speaker, Brother Guy and Jay, who spared time from his precious schedule to grace this occasion and for his valuable insights in the field of land science. Sir, we wish to welcome you all the people in yours. Bro, in fact, if festival one martin என்ன பண்ணா ஸ்கிரீன் மார்க் ரூம்ல பெரிய போறா சிட்டிங் ஓகே ஹவுஸ் அட போறீ சரி நீ அவர் கேட்டாரு Smoking for smoking. Hello, brother. Hello, brother. Brother, could you please switch on the mic, brother? On the mic. On the mic. On the mic. On the mic. Yes, of course.
brother. Hello, brother. Just a second, brother. Just a second.
Test 1, 2, 3. You can hear me now.
Hello, brother.
Can you hear me?
Yes, brother. I can hear you.
Suddenly, I can't hear you.
Can you hear me, brother?
Hello.
Hello?
Test 1, 2, 3.
Test 1, 2, 3. You can hear me now.
Yes, brother. I can hear you. Can you hear me?
Can you hear me? Yes, brother. I can hear you. Suddenly, I can't hear you.
Yes, brother. Thank you. Can you hear me, brother? We'll start in a short while, brother. Just 5 minutes, brother.
Test 1, 2, 3. Can you hear me?
Yes, brother.
Yes, brother. I can hear you. Can you hear me? Yes, brother. I can hear you. Suddenly, I can't hear you.
Thank you. Can you hear me, brother? We'll start in a short while, brother. Just 5 minutes, brother.
Test 1, 2, 3. Can you hear me?
Yes, brother.
Yes, brother. I can hear you.
Test 1, 2, 3. Now, can you hear me? I still hear nothing from you.
Hello, brother. Can you hear me?
Short while, brother. Just 5 minutes, brother. Test 1, 2, 3. Can you hear me?
Hello?
Hello.
Hello? Hello?
Test 1, 2, 3. Now can you hear me?
Hello, brother. Can you hear me?
Okay, now I can hear you.
Can you hear me, brother?
Yes, now I can hear you. My system is smarter than I am. I guess the last thing to question is if I can get screen sharing so I can share my screen and my talk.
Okay, now I can hear you.
Yes, brother. Great, brother. Just a while, brother. We'll start in short while, brother. In short while.
My system is smarter than I am. I guess the last thing to question is if I can get screen sharing so I can share my screen.
Yes, brother. I'll give you.
Okay. Find that. Let me try that.
Just
No,
a second,
still
I'll
can't.
give you. I'll just
Still can't share my screen.
Just a minute. Just a second, brother.
Oh, well. Now I can do it. Excellent. Excellent.
Can you hear me, brother? Loud and clear.
Loud and clear, and you should be able to see my screen now.
Yes, brother. I can see your screen, but before that, we'll have a short inauguration session for 10 minutes, brother.
Say again, it's not too clear. You want me to stop sharing?
Session for 10 minutes, brother.
Say again, it's not too clear. Okay, let me know when you want me to start.
Yes, brother. Just a second. We'll start in a short while, brother.
Okay.
Yeah, great, brother. ஆமா நீங்களும் அங்கதான் பேசணும் கேமரா. Okay, now we'll be starting the inaugural session, and following which we'll have the webinar. So I invite Infant to take over the session.
Space exploration is a force of nature unto itself that no other force in society can rival, said the famous astrophysicist Neil deGrasse Tyson. Good evening, everyone, and a warm welcome to Eluciphy webinar lecture series. It's truly a pleasure to have each one of you joining us today. We have gathered here as a community of students, professors, lovers of science, and space enthusiasts who share a common interest in physics and especially astronomy. Prayer lays hold of God's plan and becomes the link between His will and its accomplishment on earth, said Elizabeth Elliot. Let us start the session with seeking the blessing of God through this prayer song.
Hello all. Since there is a short technical issue, we'll not be having the prayer song. Instead of which, we'll have a short prayer. In the name of the Father, and of the Son, and of the Holy Spirit. Amen. Dear Lord, thank you for this day, and thank you for this session. Since there is a short technical issue, we'll not be having the song. We seek your blessings and guidance. Thank you for this day. Thank you for the time. Let this session sink within us, and let us love science and faith together. This we pray through the blessed name of our Lord Jesus Christ. Amen. Thank you for this day. Thank you.
The Loyola Astronomy and Innovative Club was founded by students with the aim of fostering the exchange of ideas and knowledge, while also promoting a culture of creative and analytical thinking in the field of science among their peers. Up to this point, the club has successfully released 3 editions of magazines, collaborated with different college students, and is currently organizing its inaugural webinar series titled Eluciphy Webinar Lecture Series. It is important to express our appreciation to the individuals responsible for establishing this club, as without them, none of these achievements would have been possible. Leadership entails the ability to turn a vision into tangible outcomes. I am delighted to invite the head of the Department of Physics, Dr. J. Madhavan, to deliver the welcome address in this auspicious moment.
Yes, thank you, Infant. Brother Guy, welcome. Brother, can you hear me? Respected Reverend Father Rector, Reverend Father Secretary, and Reverend Father Principal, our esteemed speaker of the day, Brother Guy S.J., professors, students, and participants. It's both an honor and a privilege to deliver this welcome address for this wonderful event. On behalf of the Astronomy and Innovation Club, the Department of Physics, and the management of Loyola, I extend a warm welcome to Brother Guy S.J., the Pope's astronomer. It's a privilege to have you here, brother, and we are hoping that this prolific Jesuit scientist will enlighten us. I also take this opportunity to express our gratitude for accepting our invitation. Once again, welcome, brother. Welcome to this event.
Thank you.
Yes, brother. Thank you, brother. I extend a warm welcome and appreciation to the convener, Dr. Arulmodi, and the student volunteers, Brother Prince, Infant, and others. Additionally, I welcome all the professors here, students, and other participants. May this event be a great learning experience. Thank you. Over to Infant.
Thank you, sir, for your words of welcome. Introductions are like first impressions. May I invite Dr. S. Arulmudi, Coordinator, Loyola Astronomy and Innovative Club, to introduce the resource person.
Ladies and gentlemen, good evening to each and everyone gathered here. It is with great honor and privilege that I introduce our distinguished chief guest for this momentous occasion, Brother Guy J. Consul Magno, S.J. His illustrious career and extensive expertise in meteoroids and asteroids promise to enlighten us on the enigmatic asteroid Bennu. On behalf of Loyola management, I extend heartfelt greetings and sincere appreciation for his esteemed presence. Brother Guy S.J. is an accomplished American research astronomer, physicist, religious brother, director of the Vatican Observatory, and president of the Vatican Observatory Foundation. His academic journey includes earning a Bachelor of Science, Master of Science, and PhD in planetary science. Following his postdoctoral position at Harvard College Observatory and MIT, he embraced the vows of a Jesuit brother in 1991. His commitment to the intersection of faith and science is evident in his extensive literary contributions, including co-authoring astronomy books like Turn Left at Orion and Worlds Apart, as well as exploring faith and science in titles such as The Way to the Dwelling of Light, Brother Astronomer, God's Mechanics, and Would You Baptize an Extraterrestrial? Additionally, he has edited The Heavens Proclaim. Recognized for outstanding communication, Brother Guy was awarded the Carl Sagan Medal in 2014 by the Division for Planetary Sciences of the American Astronomical Society. Often referred to as the Pope's astronomer, he assumed the role of director of the Vatican Observatory in September 2015. In 2022, he received the St. Albert Award from the Society of Catholic Scientists and serves on the governing boards of various international scientific organizations. As we embark on this webinar to dwell into the nature and evolution of small bodies in the solar system, particularly focusing on Bennu, the largest carbon-rich asteroid sample ever delivered to Earth. Let us eagerly anticipate the wealth of knowledge that Brother Guy S.J. is set to share with us. Without further delay, I now hand over the virtual floor to our esteemed speaker. Thank you. Welcome you, sir.
Thank you very much. And I will share my screen now. So I hope you can see the first slide. Is that correct? Okay, I assume that everything is going well and you can see my screen.
Yes, sir. Yes, sir.
Right. Share. Right, there we are. Okay. I've retitled this a little more informally as What's Surfacing on Bennu, because I want to talk about how the surface of Bennu can be described by things that are now on the surface of the Earth. As you may know, in September this past year, just a few months ago, in the desert in Utah, this sample was returned from the OSIRIS-REx spacecraft. It had been launched about 10 years earlier, went out to asteroid Bennu after orbiting it for about 2 years. They found a place where they could land. Just briefly, they touched the surface, gathered dust and rocks into a capsule, brought the capsule back to the spacecraft back to Earth, and it finally landed on September 24th. And when they opened the capsule, they discovered this. What's interesting is that, in fact, they haven't opened the capsule. What you see here is a metal disc with the screws tied into it, and then a layer of plastic, and most of the sample is underneath the plastic. But there was so much extra sample that they got a lot of it that never got underneath the sample. And when you look closely at it, you see these marvelous brown rocks. Now, there's a lot of science being done. Most of it is not public yet, and so I'm not allowed to talk about it. To be honest, a lot of it I haven't been told about yet. But with the pieces there and the parts that have already been released, we know that there are a number of different interesting materials that they have already found, both interesting in terms of the rocks and interesting in terms of the content. Now, the white bars in the bottom of these pictures show distances at the top of 10 microns and at the bottom of about 2.5 or 5 microns. You have to remember 10 microns is a bit thinner than the width of a human hair. So they're seeing small grains in the microscope, which turn out to be very much filled with water-bearing clay minerals, iron oxides, sulfides, but at least 5% of the material in this asteroid turns out to be very, very rich in carbon. Now, the interesting thing is that this is not the only asteroid that was sampled. When the American spacecraft, with European participation, went to asteroid Bennu, there was a Japanese spacecraft that went to asteroid Ryugu. And what's fascinating is that they look to be very similar in shape. There is one important difference, that in fact, asteroid Bennu is significantly smaller. But they both have this very odd shape, almost like a child's top. It's a cone in the top and the cone in the bottom. And this is not the only asteroid that has been seen to have this shape. When you have radar images of other asteroids that have come by Earth, or images that were taken by a spacecraft that was actually going on to someplace else, in the case of asteroid Steins, which was taken by the Rosetta mission, you see this is not an unusual shape. And the modelers who have worked on this think they understand why an asteroid might have this shape. It happens if the asteroid is spinning very, very quickly, so that material is spun off of the equator and then drag down, slides down to the equator where the phony force, the centrifugal force, appears to be the strongest. Then the question is, why does the asteroid spin so fast? The answer to that is an interesting force called YORP, Y-O-R-P. And YORP is a variant of the Yarkovsky effect. Now, the Yarkovsky effect is kind of odd. It was first described more than 100 years ago in a relatively obscure Russian pamphlet. Now, in 1951, an astronomer named Ernst Erpich managed to find a copy of this pamphlet, or rather, he was writing about it in 1951, about having seen it back in 1910 when he was much younger. And he just described from memory what he thought the pamphlet was saying. The idea was, if you have very small objects in space in orbit around the sun, they ought to be following perfect Keplerian orbits, but of course, nothing is perfect. What are some of the things that can force them out of their orbit? Well, they can be forced out of their orbit if they're feeling a push a little bit in the direction of the orbit or a little bit against the direction of the orbit, and that will change the size of the orbit. Now, one of those forces is the Poynting-Robertson effect, and I'll let the physicists describe that. But Mr. Yarkovsky thought of another force. Look at the picture here. Say your asteroid is spinning. And the sunlight hits the daytime side and is radiated away at night. But as it spins, the afternoon side is a little bit warmer than the morning side, just as you notice that it's warmer at 3 in the afternoon than it is at 9 in the morning. If it's warmer in the afternoon side, then the photons, the infrared photons being ejected, are a little bit higher in energy, and that will add a little bit of energy off to the left in this picture. If that happens to be the orbit direction of the asteroid, then the asteroid's orbit will gain energy and the orbit will get bigger. And if it's in the other direction, then it will get smaller. The point is it will change its orbit. Now, the effect is very small, but when you've got millions of years to work with, that small effect can build up over time. It also depends on how fast it's spinning and how long it takes for the heat to be absorbed and re-emitted. And that second thing is called the thermal inertia. But along with the Yarkovsky effect, there is something which is the Yarkovsky-O'Keefe-Radlevsky-Paddock effect, or the YORP effect, which says not only will this effect, acting more on one side than the other side, move the asteroid's orbit. If one side of the asteroid gets hotter and is emitting the photons hotter, and the photons are not emitted straight off the asteroid, but in other directions, then in fact, it will tend to make the asteroid spin faster. If it spins faster and faster and faster, eventually it gets to the point where it should be spinning so fast that material flies off the equator and it pulls itself into this top-like shape. This had been theorized. The little observation we had from a distance seemed to be consistent with how this was happening. But the curious thing is that these two asteroids were not the first asteroids we sent spacecraft to. And they were not the only shapes that we have found asteroids in. The Japanese 10 years earlier had sent a spacecraft to a very different kind of asteroid called Itokawa. And you can see Itokawa looks very different from that top shape. It looks to be a bunch of lumps, but you'll notice in the center, there's a very smooth area along with a very rocky surface. One of the interesting differences between these two shapes is the amount of light that comes off and the spectra of the light that comes off. Most asteroids can be classified into two lumps, which are called either the S-class or the C-class. And the idea is that the S-class are made out of ordinary chondrite materials, which are rocks not all that different from the rocks you see on Earth. whereas the C-type asteroids are made out of material, something close to what we call carbonaceous chondrites. And the carbonaceous meteorites are sometimes very rich in iron and in water and carbon. So objects like Ryugu or Bennu, you might think would be made of this kind of material. I just remind you that meteorites are rocks that fall from space. We're pretty sure they come from the asteroid belt. Whenever we've been able to trace their orbit, and when they hit the top of the atmosphere, you can trace it back to the asteroid belt. And meteorites come in various types. There are those that are made out of stone, those that are made out of almost entirely iron, and then there's a mixture of stone and irons. But the most common and primitive are the chondrite meteorites. They're called that because they have tiny beads of, less than a millimeter across, that are called chondrules. And the next common and more interesting primitive are the carbonaceous chondrites. So you've got ordinary chondrites and carbonaceous chondrites, and those seem to match up with the two kinds of asteroids we've got. Sounds pretty simple, sounds pretty clear. Naturally, in the real world, it's never quite that clear. The trouble is that the word carbonaceous chondrite was applied to a whole realm of meteorites that were very dark. But when you study the meteorites, you discover not all the meteorites that are dark because they have carbon. Not all the meteorites that are dark are, in fact, carbonaceous chondrites. You can roughly divide the carbonaceous chondrites, the ones that, for many reasons, for trace elements and the like, we call carbonaceous chondrites. You can divide them into two groups, Orgay and Allais and Migay. The ones above the blue line are Ci or Cm meteorites, and they tend to be rich in water and carbon, but the black meteorites below that are still called carbonaceous, you see these ones in the top, maybe 20% water, 5% carbon. The ones below don't have any carbon. They're black because they've got magnetite or other very dark minerals. So just because a meteorite is dark doesn't mean it's carbonaceous. Just because we call it a carbonaceous chondrite doesn't mean it's carbonaceous. But when you measure those meteorites that actually are on the top, like the ones above, the ones rich in carbon and rich in water, we think we're measuring meteorites that are probably like the surface of Bennu or Ryugu. And the reason we can say that is you can actually look at asteroids in the infrared and see the absorption feature of water in their surfaces, or you don't see the absorption feature of water in those surfaces. The spacecraft teams from Japan and America that chose these asteroids to go to chose them because they had that absorption feature. And therefore, it seemed reasonable to think that they were going to be full of water. Here at the Vatican, we've got a laboratory that doesn't measure the carbon and the water. We don't measure the chemistry. We measure the physical properties. It's one of the few laboratories in the world that does that, and so well known that we have other famous scientists. This fellow is in his white lab coat there. You may recognize he's an Argentinian chemist who went on to join the priesthood and do other things besides being a chemist. That, of course, was the time when Pope Francis visited our lab. In our lab, what we measure, among other things, is the density of the meteorites. Now, density is the mass of the meteorite, how heavy they are, divided by the volume. So you could have two samples, one made of concrete, one made of air, and the concrete is going to have more mass in that volume than the air is. The porosity is the amount of empty space, which is to say air or vacuum, that you have in the meteorite. And the way you measure that is you measure two different types of density. The bulk density uses the volume of the whole sample, including the volume of whatever pores or cracks or voids are in the rock. The grain density measures just the volume of the rock and not the volume of the pores. The difference tells you how much the volume of the pores is, and that tells you the porosity. That tells you how well compacted the meteorite is. How do you measure the volume of a rock? Well, how do you measure the volume of a rock, period? The easiest way is you put it in a fluid, you see how much fluid is displaced, and that's the amount of volume that the rock is. You know, in terrestrial rocks, you dump it in water, but you don't want to use water for meteorites because it will change their chemistry. Also, you really want a fluid that either completely goes into the rock or completely doesn't go into the rock. To measure the grain density, you want a fluid that goes into all the pore spaces. And what we use is gas, nitrogen gas. We've got two containers here. You put the rock in the one container, you put in the plug. You raise the pressure in one container to 2 atmospheres. You raise the other pressure, you keep it at 1 atmosphere. You measure the pressures very carefully. You open the valve and the pressures equalize. The bigger the volume of the rock, the less volume there is for the gas, and so the higher the pressure stays. And you can use, perfect spheres like billiard balls to actually calibrate how much pressure change equals how much volume. You can even now get commercial devices that measure small pieces, but what we have done is we have built our own custom device which measures slabs or the other kinds of odd shapes that meteorites can come in. And you see it circled in that picture there. How do you measure the bulk density, though? How do you measure the density of something where you don't want any of the fluid to go in? My first thought came when I was having coffee, because we're in Italy, and of course, everybody stops for coffee at 10 o'clock. And when I was pouring sugar into my cappuccino, it suddenly dawned on me that sugar, fluid, any kind of powder, could act as a fluid that goes all the way around. So if I have a cup of known volume, and I just pour in, we don't use sugar, we use glass beads, but the same idea. You pour in glass beads and you measure, you scrape the top and you weigh it, you know what the density of the glass beads are. You put in the rock, you fill the rest with the glass beads. Now you know what the density of rock plus glass beads is, so you subtract the two and you get the density of the rock. To be able to do that over lots of meteorites, of course, I hired a young Jesuit to do all the work for me. This is Brother Bob Mackey about 20 years ago. Well, Brother Bob has now joined our community, and he has come up with an even better way. Instead of pouring glass beads on the rocks, he takes an image of them, a 3D image, with a laser scanner, with, of course, his minion sitting on top of the scanner. And this gives you an even more precise measurement and doesn't even have the beads touching the meteorite. So between these two ways, we can work out what is the actual density and porosity of the meteorites. Here's the numbers that we came up with. The bulk density shows that most stony meteorites have a density of about 2.8 to 3.6 times the density of water. But notice the orange yellowish spot way off to the left here. Those are the wet carbonaceous chondrites. Those are the CIs and the CMs. Those are the ones that are rich in water and carbon. And you notice that they have a much lower density. When you measure the grain density, of course, the density is going to be higher because you're not measuring the volume of the little pore spaces. Nonetheless, the wet carbonaceous chondrites, the CIs and the CMs, still have a much lower density. And when you work out the pores, most meteorites are going to be around 4 to 5% pore space. It's actually just the cracks that you see in the rocks. But the carbonaceous meteorites, you see here 9%, but then there's a tail of these that go off to 15, even as much as 20% empty space. This meteorite, in fact, looks like a solid rock, but it is 25% empty space. And when you actually look at meteorites through a microscope, you can see that most of the pore space is due to cracks, but those dark, wet meteorites can have much higher porosities. The most porous ones are at a 20 to even 35% pore space, and that's not just due to the cracks. You can see how meteorites have cracks in them. That accounts for most of the pore space, but not for the wet carbonaceous chondrites. Now, that's not the only thing that we can measure in our laboratory. I'm also interested in how these meteorites hold their heat, because remember, that's an important factor in how fast the asteroid was going to spin and whether or not it was going to have a big Yarkovsky effect and a big Yorp effect. How do you measure the amount of heat inside a meteorite? One way to do it is to put a thermos bottle, fill it with liquid nitrogen, and as you wait, the liquid nitrogen boils away until you drop in the sample. The weight goes up, of course, by the weight of the sample, but then it starts boiling massively because the sample is hot and the liquid nitrogen is cold. And eventually you work out how much of the liquid nitrogen was boiled off. And that depends on how much heat came out of the meteorite. So now you know how much heat the asteroid would give off when it drops from room temperature to liquid nitrogen temperature. That tells you the heat capacity. There is a more clever way of measuring that using this giant machine, but this machine can also measure the conductivity, so that you have a little slice of a meteorite, very small slice. You put a heat pulse and you measure how long it takes for the heat to travel from one end to the other. This is a machine that our colleague Sayo Peel is using at Boston College, the Jesuit University in Boston. Between these two machines, we are able to measure the heat capacity, the conductivity, the density, and the porosity of the CM meteorites. And now we're going to compare them to what we think we see on the surface of Bennu. These were the first 5 that we measured. You can see that most of them are very porous, relatively low in density. When you measure their thermal conductivity, that green line is what you expect a normal rock, a nice crystal, to do. But the meteorites that we have don't even look at the red line or the green line, but go all the way down to cold Bakkeveld at the bottom. You can see that the conductivity of a CM meteorite is 10 times lower than what you would have expected for a normal rock. And that's because it's full of cracks. Heat tries to travel through the rock by making each molecule make the next molecule vibrate and vibrate and vibrate. But as soon as it runs into a crack, it's then got to go all the way around the crack to find a way to keep sending the heat on the way through. And that means that it has a much longer distance to travel, which means it takes a much longer time for the heat to actually get from one side to the other. Because the CMs are so porous, they have a very low thermal conductivity. And these are the 5 that we measured more recently. Now, the heat capacity, you can use Sayo Peel's machine to measure the heat capacity as well. And you see these nice curves which show that the heat capacity, it actually holds heat better when it gets warmer. That's not surprising. But Sai noticed that when you actually look at how the heat capacity changes, those dots are the first derivative, and it's not a smooth line. There's a little bit of a dip at around 220 to 240 Kelvin. And he thought, well, that's a nice curiosity, but, you know, it's not so much that you'd really notice it. He didn't think much of it at the time. That's the region where you find that dip right through there. And you can see in the actual curves, it's hardly noticeable. If you know the conductivity and you know the heat capacity and you know the density, you can calculate a number called the thermal inertia. And the thermal inertia of these guys is very low compared to a rock. But here's the odd thing. We knew the thermal inertia of asteroid Bennu. And because we could measure that using infrared telescopes even on Earth. And low as the numbers were for our meteorites, it's even lower for Bennu, by a factor of 2. The curious thing then is, why would it be so low? Remember that this number depends on the density. Well, that's not going to change. It depends on the heat capacity. That really just depends on the minerals. That's not going to change. And it's going to depend on the conductivity. The more cracks you have, the lower the conductivity, the lower this number will be. So it looks like on the surface of Bennu, we're not even seeing solid rocks. We're seeing maybe a dusty surface. That's what the people thought when they designed the spacecraft that was going to go to Bennu. That they would get there, they would find a very dusty surface. It would be really easy to collect that dust into their container and bring it back to Earth. Because the global average of the thermal inertia was so low. Well, this is Cy Peel again. He happened to have in his lab a little gizmo that would allow you to measure another thing about these rocks, which is the coefficient of thermal expansion. Now, what's that? If you heat a rock or a piece of iron or just about anything, as you heat it, it gets a little bit bigger. Not by a whole lot. Maybe 1 part in a million. 1 degree means it's 1 part in a million bigger. Nobody had ever bothered to measure this for a meteorite because they're rocks. And the coefficient of thermal expansion of a rock is really small, 1 part in a million. Why waste your time doing this? But Cy had the machine. He had the little gizmo that could make the measurement. And he decided, what the heck? Why not make the measurements? And this is what he found. As you go from very low temperatures up to about 200 Kelvin, sure enough, it rises by about 1 part, 5 parts per million. But then at 200 degrees Kelvin, as you start to heat it up, it actually gets smaller rather than bigger. That's bizarre. And it gets smaller by a whole lot rather than bigger. What's going on there? Well, we start digging in the literature. What would make something get smaller as you heat it up? And it turns out this happens for minerals that have water in them. When you get to 200 degrees Kelvin, the water molecules are finally mobile enough that they can rearrange themselves into a tighter configuration, and that causes the mineral to suddenly shrink a whole lot more than it was growing. Then as you heat it up, they start to randomize themselves and they go back to pretty much where they were before. But between 200 degrees and 250, 260, you're going to have these rocks shrinking a whole lot and then growing again. Well, that's curious, but, you know, it's kind of weird. Incidentally, that was right where we saw that strange change in the heat capacity, so we should have known something was going on there. There was a phase change in the rocks. Now, at this point, you're saying this is all very interesting little, detailed physics of rocks, but I'm interested in Bennu. I'm interested in that asteroid. What does this have to do with the asteroid? Well, for one thing, notice that, okay, the heat capacity and the thermal conductivity and the thermal inertia are really different at these low temperatures. There's a strange size change at 235 where things were going to contract. The hydrous minerals are going to cycle through at 235. And, if they were cracking, if something was causing them to shrink and then grow and then shrink and then grow, wait a minute. Wait a minute. These are materials that are on the surface of an asteroid out beyond Mars, where the temperature is not a nice, comfortable 300 Kelvin like it is here on Earth. 300 Kelvin is room temperature, it's 20 Celsius, 23 Celsius. 300 Kelvin is what we have on Earth. But in the asteroid belt, it can go to below 200 Kelvin at nighttime to about 250 Kelvin during, oh, wait a minute. Oh, wait a minute. Every time it spins, the surface is getting hotter, then colder, then hotter, then colder, and it's spinning every 4 hours. Not only that, they are in orbits that are not perfect circles. The average temperature as you get closer to the sun in the perihelion is going to be much warmer than the average temperature 4 years later. So you're going to have this heat pulse that has 4 years to penetrate into the rock and then out again, causing them even more deeply to shrink and grow and shrink and grow. These rocks are going to start fragmenting themselves. And here's why that's important. Because you see, there was a problem when they got to Bennu. The thermal inertia of Bennu told everybody that the surface was going to be made out of dust. But as soon as they got there, they saw that it was completely covered in rocks. In fact, that's why they took more than a year to try to find a place that was smooth enough that they could put this lander down there. All right, so they put the lander down. This is what happened when the Japanese put the lander down, and suddenly all sorts of rocks, much more than you would expect, flew up. And when they landed on Bennu, and they put the lander down, expecting that the lander would hit a solid surface, it in fact blew everything up into dust. What's going on? How did that happen? How does it happen that you've got a surface that looks like it's covered in rocks, but in fact, when you touch it, it turns into dust? Well, we knew, or we thought we knew, that it was covered in a thin regolith, this dusty surface, because of the thermal inertia, which depends on the porosity. But wait a minute. Why is there a dusty surface on an asteroid in the first place? Remember that rocky asteroid, Ichikawa? The one that seemed to have a real sandy surface and didn't have such loose rocks that it was spun up? It's made out of solid rocks. Every time a micrometeorite, a bit of dust, the same thing that makes shooting stars in our atmosphere, every time one of those hit a solid rock, it would break a little bit of the rock off, creating dust on the surface. But let's say the thing that looks like a rock on the surface of Bennu actually isn't a rock anymore. It's completely and thoroughly broken apart by these thermal stresses, by going in and out, expanding and contracting, once every 4 hours on the surface, and once every 4 years as you go even deeper, because depending on when the heat cycle is going into it. So even though it looks like a rock, it's not going to fall apart. There's no gravity to fall it apart. When a micrometeorite hits it, it's so soft that the micrometeorite just goes straight through the rock and out the other side. That appears to be what's happening to asteroid Bennu. So even though it looks like it's covered with rocks, where the small impacts would have turned those rocks into dust if they were rocks, the fact that the rocks have been flexing the way that we find in the lab means that the micrometeorites just goes right through them and they may remain looking like rocks. So, is that actually what we're going to see in the Bennu rocks? There's Bob Mackey, the same guy I showed you 20 years ago when he was my minion. Now he's a top scientist, still a Jesuit brother, still at the Vatican Observatory, but they have invited him to go to the Johnson Space Center to install this machine that you see him building that will measure the density and the porosity of the Bennu samples. They're waiting for the samples to be released, and within the next couple of months, we hope that we will be able to measure the density of these rocks, the porosity of these rocks, the heat capacity of the rocks. Are we going to see a little dip like we saw for the CMs? And if they are solid enough, which maybe they won't be, we might even be able to measure to see if they shrink when they hit 200 Kelvin and then grow again. So stay tuned. These are the pieces of Bennu, rich in carbon, rich in water, and rich in a lovely little mystery as to why they still look like rocks, even if they've been flexed so much. That's what we hope to find out in the next year. And that will tell us what's surfacing on Bennu. So thank you very much. Thanks for listening to me. And if you want to know more about the work we do, just go to our website, vaticanobservatory.org. And at that, I'd be delighted to take any questions you have.
Thank you, sir, for exhilarating information. That explained a lot and what are the research going on, and that was wonderful, sir. Thank you. The speech has promised to be an enlightening and intellectually stimulating experience for all of us. Once again, thank you.
Thanks for having me here.
Thank you. Mankind is drawn to the heavens for the same reason we were once drawn into unknown lands and across the open sea. We choose to explore space because doing so improves our lives and lifts our national spirit. Let us combine the journey, said the 43rd President of the US, George Bush. The success of this event lies not only in the knowledge shared by our experts, but also in the vibrant discussions and interactions that will unfold throughout the session. I encourage each of you to actively participate, ask questions, and engage yourself with our distinguished speaker. Please type down the questions in the chat box and our team will present them to the speaker. Since we do not have much time, please make it fast. And even if Storm does not permit, we will mail our speaker with the questions that are unanswered and we'll post the answers in the group. Now the chat box is open. Feel free to drop your questions.
So I see the first question, which is quite interesting. Does the Yorp effect have effects on the mineral composition? And the other way around, the mineral composition will affect how much and how strong the Yorp effect is, because that Yorp depends on how long the rock will hold on to its heat before it re-radiates it. And that depends on the minerals. The actual amount of heat it's getting from the sun is way too tiny to change the mineralogy. It's only changing it by 10 or 20 degrees. But it certainly, the minerals themselves tell you how strong the Yorp effect is. Can we expect more rocks like this in the Oort cloud? Probably. The Oort cloud is where the comets come from, and we're beginning to measure dust from comets. Now, we can tell dust that hits the Earth's atmosphere and makes shooting stars. We can tell whether they're from comets or from asteroids by how fast they're moving. You can actually measure how fast the piece of dust is when it hits the atmosphere. And while it's true that the chemical composition of the dust is a little different from the rocky meteorites, it's full of the same elements, carbon and hydrogen and oxygen and nitrogen, that we find in the CM and CI meteorites. So there's some argument as to, are these meteorites really from bodies that were once extinct, once comets, and they lost all their ices and they just became extinct cores. So it could very well be that comets have very much an effect like this. Are there any new elements that have been found? The actual elements that you find in the periodic table are the same whether they're on Earth or on the moon or in the asteroids or in the meteorites. But what's different are the proportions of the elements. Some elements are very rare on Earth, elements that make up iron, or that make up metals. Most of the metal in the Earth went into the Earth's core, and it carried with it all of the other, or most of the other elements that are metallic, elements like gold, like platinum, like silver, which is why they're rare on the surface of the Earth. They're actually much more common, not so common you're going to get rich, but more common numerically speaking. The other thing that's very different is the isotopes. I'll give you an example. Oxygen is an atom that has 8 protons. And because of 8 protons and the 8 electrons that balance it, that changes the way it reacts. If you get rid of an electron or 2 electrons, then it's makes oxygen a very reactive element. But along with the 8 protons, usually in oxygen in the nucleus, you have 8 neutrons. And that makes what we call oxygen 16. That's the most common oxygen in the universe. Sometimes you have an extra neutron, and that makes oxygen 17. Sometimes you have 2 extra neutrons. You have oxygen 18. What happens if you have 3 extra neutrons? Then the nucleus becomes unstable and it decays. Well, the proportion of 16 to 17 to 18 in Earth rocks is significantly different from the proportion that you find in different meteorite types. In fact, you can classify a meteorite by the ratio of 16 to 17 to 18. So in that case, we know that these are rocks that have seen interesting regions that are different from the material that made up the Earth. Let's see, are the perturbations real or hypothetical? We've actually seen the perturbations. We have actually been able to measure some asteroids as they were spinning up because they came close to the Earth. You could measure their spin rate with radar, and then the next time through, you could actually see their spin rate changing just about the amount that we predicted through this effect. So we're pretty confident that this Europe effect actually is occurring. Does studying asteroid Bennu shed light on our understanding of the early solar system? I think so. The fact that we have meteorites at all means that these are well-compacted rocks. But where did they get compacted? Between Mars and Jupiter, there's only 0.1% of the material that you would expect to be there if you could, explain the amount of material that went into making Earth and the amount of material that went into making Jupiter. How come there's not that same amount of material in the region of Mars and the asteroids? Jupiter ejected it. Jupiter's gravity cleared out most of the asteroid belt. In the process, it broke things up. And that meant that asteroids, even the stony one like we saw, the Itokawa, have been broken into small bits and reaccreted. Studying these asteroids tells us just how violent the early solar system was. Why do we use nitrogen in measuring the density? Well, I want a gas that can get into all the cracks and not make any chemical reactions with the rest of the rock. The first few years that we did this, we actually used helium gas. Helium, however, is very expensive. And to make the tubes that can hold the helium without leaking is very difficult. After we'd made a bunch of measurements with helium, we went back and tried nitrogen, which is a lot cheaper and a lot easier to work with, and we got the same results. So we said, okay, we can use nitrogen and be just as accurate. Are asteroids formed in the time of the early solar system like fossils of the early solar system? Exactly. Exactly. That's why we're so excited to be able to study the rocks that come, because these are like looking at pieces of what was going on in the early solar system 4.5 billion years ago. Do we see this kind of effect in any other meteorites? Not yet. But here's the thing. We've only started looking. Remember how I said that, Cy Peel, who made the first measurements, did it just because he happened to have the piece, and everybody was telling him, don't waste your time. We know what the answer is. The answer is going to be boring. Well, now that we know the answer isn't boring, it's time to go back and measure some other meteorites. So it'll take a while to really come up with that. Can we change the direction of the motion by using a fission, by blasting a bomb? I suppose we could. You've got to be very careful about, blowing up the side of an asteroid. The easier thing is actually to have a spacecraft blast itself into an asteroid. A year ago, there was an experiment that did exactly this. They found an asteroid, small asteroid, that had a tiny moonlet. And they could measure how fast it took for the moon to go a complete orbit. You could even observe that from Earth because it changes the brightness as the moon goes in front of or behind the asteroid. So you can time its orbit. Then they ran a spacecraft into that moonlet to see how much it changed. Out of that, they have a sense of how much energy you need to impart into one side. You want the stuff to blow off in one direction to be able to give it a push in the other direction. And now that we know that, we could possibly change not so much its spin, but its orbital period. So if we see an asteroid that we calculate is, got a 50% chance of hitting Earth in the year 2100, let's say we found an asteroid like that, you could go out there, slam it with just enough energy that it's now into an orbit that we're pretty sure is going to miss. Here's why you don't want to do that when the asteroid is getting close to us. If the asteroid is about to come in and it's got a 50% chance of hitting it, and you go up there and you try to blow it up into a schmillion pieces, you go from 50% chance that it will hit to 100% chance that half of it will hit. That's not an improvement. But it's worse than that. Because remember how I said if something is porous, then you can try to hit it and it just absorbs the hit. If all you're trying to do is to break it into pieces, you're not going to be very efficient because it's already broken into pieces. So rather than breaking it up, you want to actually push it to one side. Let's see, let's go back. Does the sample contain organic compounds? Oh my gosh, yes. Could it have influenced the origins of life? Maybe. Here's the thing. On Earth, there are, I'm remembering this off the top of my head, a biologist will tell me 17 or 18 kinds of amino acids that are involved in life. You find many, many more types of amino acids in these rocks because they were not formed by living creatures that only make certain amino acids, but they were formed by chemical processes in ultraviolet light that can make all sorts of amino acids, including some that have a chirality of right-handed versus left-handed. And I didn't mean to do that, I guess. And that means that we're importing the raw materials, but we're probably not actually importing life itself. Could it sustain microbes? Well, I don't know enough about microbes to know. I wouldn't say that it couldn't. I will say this, that we've found amino acids we have never found in any of these meteorites to date. Anything that looks like a microbe. Okay, going from an amino acid to a microbe is a huge step, and nobody's figured out how does nature do it, much less how can we do it. Of course, that's one of the things they'll look for in these samples, and one of the reasons why these samples are being kept very carefully in, airtight boxes, so that you're not just carrying them in the lab and wandering around with them. Is there any chance of Bennu hitting the Earth? Not in the next couple of 100 years. As I say, they change their orbits because of the Orp effect, so you keep an eye on them, but it's not considered one that, is really likely to see it. It still could have. Can you have life carried? Remember those cracks? Remember the cracks I showed you in the meteorites? Those are just wide enough that if they came from a place that had microbes, the microbes could be inside them. I don't think you're going to find microbes in an asteroid. But Maybe you'll find them on Mars. Maybe in ancient Mars, there were little microbes. And there are meteorites on Earth that have cracks that are big enough that microbes that we know about could conceivably have been carried from Mars to Earth. Some people actually have come up with the idea that life started first on Mars and came from Mars to Earth. Is it true? Who knows? On the other hand, you know that life on Mars, the daytime on Mars is 39 minutes longer than daytime on Earth. And don't you really feel every morning when you're lying in bed, you could use another 39 minutes of sleep? Maybe we're actually Martians living on Martian time. Okay, I'm joking, but who knows? It could be possible. Where am I now? Let's see. Life carried inside it. Find asteroids, active fossils. It's very hard to get stuff from the Oort cloud. The Oort cloud is 100,000 astronomical units away. It's easier to wait for the asteroids to come to us. Do they contain polycyclic aromatic hydrocarbons? Well, yes, some of them do. One of the ones that we've studied carefully from Mars had those, and some people said, aha, it's evidence that there was life on Mars. And somebody else said, yeah, but wait a minute. We collected that meteorite from the ice shelf of Antarctica. And how did we do that? We drove up there with a skidoo, with a snowmobile. And what was the snowmobile doing? It was burning gasoline that emits polycyclic aromatic hydrocarbons. So we are always worried about how much of these organics that we see are actually from the rock itself and how much of them are contamination from when we collected it. That's another reason why it's really important to have these samples from asteroid Bennu. We'll see if they have PAHs. I don't know yet. Meteorite dissolve into several components. They do all the time. Every time a meteorite hits the top of the Earth, that air that it hits feels like a solid wall because it's going so fast. It's moving faster than the speed of sound in the air, so the air doesn't have time to get out of its way until the meteorite slows down to the sound speed. And that means that it creates a shock wave that breaks the meteorite apart. And very often you find meteorites not as one rock, but a whole field, a strewn field of rocks. Why are the surfaces of asteroids so different? And could we have the surfaces of planets? The planets, are sort of the average of all the asteroids that fell in together to make them. But basically, that's what we're trying to do in planetary sciences, to understand those surfaces. There's by no means do we understand what's going on there. There's so much to learn, and the more we learn, the more there is still to learn. So I hope that, people in this group someday might be inspired to get into planetary sciences. I don't have to tell you, India's got a fantastic planetary science and space program, and there's all sorts of opportunity. So by all means, get involved and be the next generation of people to say, I wonder what, and I wonder how. Thanks a whole lot for having me here. I guess I probably run past my time, but I'll let the host tell me when it's time to go away.
Okay. I thank the participants for a diligent and dynamic participation, for creative questions, and making this an exuberant session. Now, gratitude is a powerful catalyst for our happiness. It is a spark that lights a fire of joy in your soul, said Amy Collett. May I invite Kishore, President, Astronomy and Innovative Club, to deliver the vote of thanks.
Thank you.
Yes. On behalf of our Astro and Innovative Club, I deem it a great honor and privilege to propose the vote of thanks on this memorable occasion. I take this opportunity to express my deepest sense of gratitude to our speaker, Brother Guy S.J., who spared time from his busiest schedule to grace this occasion and for his valuable insights in the field of planetary science. Sir, we wish to collaborate with you more in the future endeavors. I thank the Loyola College management for permitting us and for supporting us. Next, I thank Dr. J. Madhavan, Head Department of Physics, who supported generously to make this event a resounding success. My heartfelt thanks to our club coordinator, Dr. S. Arunmori, and our mentor, Dr. M. Dinesh Reja, for their constant guidance and encouragement. I thank all the teaching and non-teaching staff of the physics department for helping and supporting us. I thank our technical team for their tireless effort in making this event an astounding reality and for the smooth functioning of this event. I also thank our club members who gave their great efforts to achieve this success. Last but not least, I thank all the participants who attended this lecture, and I hope this lecture would have enlarged your vision and knowledge. Thank you once again.
Thank you, Kishore. Space is a new place and a trace for the future race. Unveiling the maze and the beauty of the stars we gaze. With profound insight, we end this day. May we come together in another event like this. Stay tuned. Until then, signing off from you is CM Infant Nishant, Loyola Astronomy and Innovative Club. Thank you. Thank you, sir.
Thank you.